on the YouTube? Okay, the recording has started. I'll check whether I have posted yesterday's lecture on YouTube. Otherwise, I'll do the same for both of these, yesterday's and today's lecture. You would also let me know the best of the times wherein, not today now, but tomorrow afternoon onwards, when can we have a lecture? Please let me know. Today I have a doctor's meeting. Anyway, so I'll start immediately with what we were doing yesterday, rather what we stopped at yesterday. And it was this, right? And let me just complete it. I think we have pinned this. You can see the diagram in front of you, right? Hello. Can you see the diagram in front of you? The picture?
Yes, sir.
Hello. Yeah. Okay. Thank you very much. I've purposely put up the names in Marathi as well, basically because a few of you all could have done this in Marathi at your earlier classes, that's in school. Just go through that. Just try to identify any of these names that you can recollect. We said yesterday that there are 7 pressure belts in all. And as far as these pressure belts are concerned, these are related to the temperature differences. The temperature differences are related to the availability of heat, the various factors which are responsible for the variable distribution of heat all along the globe, which initially is divided into the 2 hemispheres and then consequently various regions accordingly. Now, there is one thing that we have to keep in mind, that we are keeping the Earth straight basically because of a geographical convenience. Otherwise, we all know that the Earth would have been like this, and these very things would be like this. This is one common logic that you have to keep very in your mind. When I said it is we are taking. Otherwise, actually, the other understanding the whole process would have been a bit complex, I would say. And that's why, even in the best of the books, you'll find it in this particular way. That is, this particular. That's one thing. Now, in your books in earlier classes, you have done pressures belts as a different topic. In NCERT books, I would say you would have done circulation of atmosphere as a different chapter. You must have done global winds as a different chapter. Let me tell you that all of these are related to each other. I spoke about this yesterday also. And once you link and have a logic of all of them, you don't even have to think about them separately. They automatically fall in places in such a way that it comes to you so very naturally as such. So that's one thing I would like you all to remember henceforth. One is that the Earth actually is tilted, but we take a liberty of keeping it straight so that we can understand it well. And secondly, these are actually winds and pressure belts are actually belong to a particular system only. It's only that for our convenience, again, we divide them into chapters. I would be doing it in a sequence so that I will not distribute it into chapters. In fact, you won't have a separate chapter on winds in your syllabus. Okay, it's just a mention of it, and so we will have to go accordingly as such. As I said yesterday, that earlier it was not believed that we could have so many pressure beds as such, because of the fact that the earliest of the people who were working on this, they said that there is only one atmospheric circulation cell, as it is called, convection. All of this is based on convection, they said. And as far as this convection is concerned, it is believed that the insolation, we saw that the insolation, the heat sun's energy is maximum here. So that is going to heat up here. Okay, so what happens is air from here will rise like this, up. It will rise like this, and then it will move in the direction of the coldest parts. On the way, it will get cold. Near the poles, it will get the coldest, so it gets blue in color. And then it will return back to the equator. And this is how the cycle or the cell is, convection cell is complete. This is called as the unicellular model, one of the earliest of models, I would say, and was given by a person known as Hadley. You'll remember him basically because he comes into reference the other way also, in other issues also. However, it was realized that it is not three pressure beds. That's one H here, high pressure, one H here, high pressure, and one single low pressure here. It was not three pressure beds, it was seven pressure beds. And in fact, here again, you'll see this part is the single cellular thing which was thought of, that the warm air here rises because of its temperature, and then it moves towards the poles, and from there it comes down to the surface, and then it moves back again to the equator. But it was realized that it is not one cell. In fact, it is divided into three cells. Okay, 1, 2, and 3. And of these three cells, you'll see that the one nearest to the equator is called as the Hadley cell. That's why I said that this is how you remember that Hadley, yes, he gave us this particular idea. But later, when we found out this, he was honored by naming this particular cell by his particular name as such. And the one near the mid latitudes is called as the ferrule cell, and the one near the poles is called as the polar cell. So these are three cells. So from unicellular, the idealized circulation is the tricellular model. Again, as I said, that things are not as easy as we see them in diagrams as far as climatology is concerned. The most simplified versions of them are made available to us. But let us go on with that. Now, you have winds that you can see here. You have the trade winds. Okay, this is the equatorial doldrums. Okay, you have subtropical high latitudes, and then you have the polar front. Now, what are these three? These three are borders between the respective cells. Say for example, between the Hadley cell in the north hemisphere and the Hadley cell in the southern hemisphere, you have the equatorial low, or what is called as the doldrum. Now, why are they called so, etc.? We'll go into the details of that. Then the boundary between Hadley and ferrule cell is the horse latitude. Okay, both of them are called as the belts of calm. It's very calm here, and that's why they're called as the belts of calm. Why are they calm, etc.? We'll come to that as such. And then you have the polar front, which is a very active front as such. I'll be discussing about this polar front also. So on a very broad scale, this is how the atmospheric circulation is. We are going to go into the details slowly so that you don't miss out or don't confuse. I'm just giving you a broad idea. Okay. This is another view of it. Instead of taking it in a three-dimensional view, we are looking at it in a two-dimensional thing as such. Okay. I will, now you'll see that this one here, okay, there is another name to what we were referring to, the doldrums here. It's also called as the ITCZ. Many of you all would be knowing about this. The ITCZ, the Intertropical Convergence Zone. And the third name to this is also called as the thermal equator. So we have two sort of equators as such. One is the absolute equator, the normal equator as such. And then there is one which is in relation to climatology. Okay, and that's called as the thermal equator. Okay, and is also called as the doldrums. It's also called as the intertropical convergence zone, and so on and so forth. Okay, now here you'll see that the winds and their directions and the movement is a bit started to get a bit complex. But as I said, we'll come back to this later, and let me once again give you another picture before we actually start looking into how actually this happens. मॅडम माझं लेक्चर चालू आहे, तुम्हाला थोड्या वेळाने फोन करू. So we need to take one hemisphere at a time, and you will see what is happening in this particular hemisphere. Okay, so I'll just put it in the right way here. Okay, this is the hemisphere we would be taking into consideration. I would like you all to actually first look at these convective cells that you can see into the atmosphere. Okay, what is happening is that here, the equatorial part, we have these red ones, red arrows going up, and then they turn blue, and then of course they come down here in the high pressure regions. Similarly on the other side. Okay, this part here, you have very cold winds which are heavy, dense, and they come down and they settle and then move towards this area. And the warm winds from this area, the relatively warm winds from this area, okay, they move towards the poles. These come from the poles, and then you have I would say sort of a friction between them, and that is why it is called as a front. The reason it's called as a front is because they have a friction, and that leads to formation of another cell. Now, being science students, I would dare to go a bit further and say that this one, what we have named as the Ferrel cell here. I hope you are able to see my cursor. The Hadley cell, sorry, the Hadley cell here, and the polar cell here. Both cells are thermally induced. Now, what is thermally induced? We'll slowly get to know about it. I'm just giving you a very broad base work around it. And the central one, the Ferrel cell, is dynamically induced. Okay, so what all this means, we're going to go into the details of that, and that's why I've kept a blank slide. Now, for all practical purposes, I will draw the Earth in a hemispheric form, but it's a north-south hemisphere. I would say I would, in fact, instead of putting up the whole Earth, what I'll do is I'll put it in a sector. So let us look at it this particular way. This is the equator. This is the pole. One section we have taken. Now what is going to happen is that the insolation is going to be very high here. Okay. Whether the sun is in the northern hemisphere, that's the summer solstice. Whether the sun is in the southern hemisphere, it's the winter solstice. Whether the sun is in equinox positions. Okay, one area wherein it is going to be comparatively perpendicular. It will not be perpendicular, but we'll see that it's going to be having an angle of 70, 75 plus regularly, is the equator. If you're going to have so much of insolation, we'll see that as far as the air particles here are concerned. Okay, I just dot down a few air particles all around. Yes, this is the atmosphere. This is going to be thicker here, and we all know that this is going to get thinner when we go to the poles as such. Air particles start getting warm, and we know what happens to any substance that is getting warm as such. Okay, you'll see that the molecules start getting vibrating, and because of the vibration, the temperatures increase. Because of the increase in temperature and the vibration, you'll see that they get lighter. Because they get lighter in density, they start ascending. Okay, so what is going to happen is these particles are going to move upwards into the atmosphere. Now, when they move it up, okay, we all know that we yesterday saw that as you go away from the surface, the temperatures are going to fall. So one, the movement upwards is going to use up their energy, and two, there is no supply of new energy because they are going up. So by the time they come to the troposphere, let us say, to the end of the troposphere, sorry, tropopause, they are very cold. They come here. The first particle which was heated up and has been sent into the atmosphere has now reached the tropopause. It's cold, it's heavy, it wants to come back. But we know that this process of heating is a continuous process. So it's not the only particle which has gone up into the air. There is a string of particles which is being sent one after the other, one after the other, one after the other. And that is what we have learned is that convection is all about. Okay, a string of particles is going up. So this poor particle which has reached its best it can go, and it wants to come back now because of its weight, however is not being allowed back because the particle following has some energy left, and that some energy is restricting this zero energy particle from coming down. So this particle has no other option, so it is pushed towards the poles. It starts its journey towards the poles. Now, theoretically, as Hadley had put it, it should go all the way to the poles. However, you'll see that this distance between the equator and the poles is huge. And if you have studied harmonic motions, you'll see that the waves in the harmonic motions, you'll see that many things are here need to be related to geometry as well. So you'll see that while this is 0 degrees and this is 90 degrees, okay, you're going to have somewhere here 30 degrees of latitude, you're going to have 60 degrees of latitude. Okay, so this is very similar to a geometric arrangement 0, 30, 60, 90. And it so happens that these particles start moving towards the poles. And by the time they come to around 30 degrees, okay, they tend to be allowed down to the surface. They're cold, they're heavy, so gravity pulls them down and they come down to the surface as such. And from here, some of these move in this particular direction, some of them move in this particular direction. Now let us speak about this particular thing. What has happened in this cell? Particles have moved up. Particles have slided sideways up in the atmosphere. This is ground, this is atmosphere. Then particles have come down, and then one section of it is moving towards the equator. Now, though I have drawn a complete square, let me tell you that it doesn't have to reach all the way here. By the time it reaches here, it already starts getting hot, and then somewhere here itself, it starts moving up, and that's why you're going to have a band here. Now, what is this band about? I'm coming to that. I'll first explain this. This now happens to be a thermal convective cell. Thermal. Now, how is it different from others? We are going to see. Okay. Now, why this is thermal? Because all of this has operated because of very high temperatures at the equator. That has pushed all these things to happen. Okay. As I said, that these particles start moving up a bit away from the thermal equator. A similar thing is going to happen in the southern hemisphere. As they approach the equator, they start going up, leaving a band of area which is not going to be moving horizontally. Moving horizontally. Actually, it moves vertically. All this is going to move vertically as such. And I would say what I was discussing could be taken up as the last arrow, last string of particles are going up as such. In that band, the whole band, the upper end of the band, the lower end of the band as such. Now, we have to understand that each of them has a significance. This arrow is known for going up. This arrow is known for coming down. Now, because this is going up, this will release the pressure on the surface. This will release the pressure of the air on the surface. Because it releases, the pressure becomes low, and you're going to call this as a low pressure belt. Exactly opposite to this, around 30 degrees of latitudes, these particles which have come down will increase the pressure in that area, and that's why that is called as the high pressure. Remember, in low pressure and high pressure zones, air particles are either moving up or they are moving down. The movement is vertical. All pressure belts, which is 0 degrees low pressure belt, 30 degrees high pressure, 60 degrees low pressure, 90 degrees high pressure. All these pressure belts will have vertical movements upwards or vertical movements downwards. Let me can show you here. Okay, I will show it to you in this diagram. Okay, low pressure, vertical movement upward. Okay, see, you'll see that the zone, it's a zone, it's not a line, it's not a compartment that you just can peep into it. This is going to be a zone of few tens of kilometers, and in each zone there is a gap. Okay, this gap, this gap, this gap. Okay, even further up you are going to have a gap here as such, and that's why it's called as a zone: high pressure zone, low pressure zone. But interestingly, in low pressure, the pressure is released, and you'll see that the air particles are going up. In high pressure, the pressure increases because these particles are coming down. Same thing happens 60 degrees low pressure, same thing happens 90 degrees high pressure as such. So, of every convective cell or square, the sides are going to be where the air is moving up or down. And of course, the other two is going to be where you're going to find these moving horizontally. This horizontal movement of air particles, what? This horizontal movement of air particles, this horizontal movement of air particles, that is this part. Now, what I'll do is I'll just try and erase this, sorry, and erase this for you, and once again draw it for you, that things are going up. Okay, that's this, we're going to have low pressure, and this is vertical movement. This is going to move sideways. This is vertically up. This is vertically down. So we're going to have high pressure. And this arm, this is the important arm. This is the arm wherein the cold air particles from high pressure move towards the warm air particles, towards the warm air regions, zones. This is nothing but your global winds. This has to be very pakka in your head. Okay, so pressure belts and winds are related to each other. Vertical movements of air particles cause pressure belts. Horizontal movements of air particles near the ground, remember. Now there are going to be some movements which happen up in the air. You don't have it in your syllabus. Those who are interested can search for jet streams, JETSTREA. They can search for jet streams and have a further reading, but this is not a part of your syllabus, so I'll not go into the details of that right now. Okay, so this is one cell. This was the Hadley cell, as we called it as such. This is also a thermal cell, basically because it is induced because of what? It's induced basically because of the warm temperatures. So if something is going to be induced because of the warm temperatures, obviously because of extremely cold temperatures also, we could have a cell which could be induced. Yes, towards the poles, another thermal cell. What happens here in the poles is that the air particles, they are get, because of the very cold temperatures above the poles, on the poles. And of course, remember, if you go up into the atmosphere above the poles, it's going to be further cold. If it is going to be minus 10 on the surface, it could be minus 50 at around 8 9 kilometers from the surfaces. So the particles are going to be hell cold, and of course they're going to be hell heavy because of the density. They're going to come down on the poles. Okay, I'm drawing this here. They're going to come down as such, and they're going to keep coming down. One particle, two particle, 100,000, 10,000. Now you'll see that if you're going to have particles dropping from some point here, okay, and they are made to gather, what is going to happen? Okay, you'll see that initially a small mound will be formed, then a larger mound, and then the larger mound, till the point it maintains a balance with gravity. After it stops being say uh, inertiative, gravity is going to pull these particles. A similar thing happens is gravity allows these particles or pulls these particles towards the lower latitudes. That is what happens. Okay, you must have seen people pile up, I would say, heaps of grains or a heap of cement or heap of sand, etc. You see that you keep on pouring sand on a heap. You'll see that until it comes to a particular level, you'll find the heap forming. Then you'll see that new coming particles are going to escape and they are going to move along the sides, and you'll see that the area of the heap grows as, okay, not in exact sense, but something very similar to that happens. That very cold particles come down onto the poles. Because they create a weight here, you are going to have a high pressure at the poles. And you'll see that those who have started in an environment of minus 50, 55, now all these are hypothetical figures, minus 55 degrees centigrade, come down to the surface to minus 10, and then they start moving toward the lower latitudes. Obviously, they are going to get warmer. Okay. And then something is going to happen which is going to make them move further up as such. What is that? What is going to happen? Okay. Now we come to the third aspect of the whole story. That these particles, it's these particles, which had come down now, some of them are moving toward the equator. A sizable number of them are moving towards 60 degrees. So they start moving towards 60 degrees. Now what happens is at 60 degrees, and that is why you'll see I'll again give you the explanation in the picture as such. It's called as the polar front. Polar front. Front in the sense comes from the word military, comes from the word military organizations. Okay, two armies standing in front of each other. What has happened along 60 degrees now? The cold particles coming from 90 degrees have warmed up a bit and they reach 60 degrees of latitude. See, this is so very fantastic that something that we have learned and we keep learning later in the form of geometry is already so very there as far as nature is concerned. Anyway, coming back to the explanation. While they are reaching 60 degrees, there is another group of air particles which has started moving from 30 degrees and it is also reaching 60 degrees from the other side. Now, though these particles coming from the polar areas, okay, sorry about the disturbance. Now, what happens is, yes, the particles moving downwards or towards 60 degrees from the poles gradually get warmer. You see that particles moving from 30 degrees are relatively warmer. Are relatively warmer. And yesterday I spoke about relativity. So in this context now what happens is, particles coming from here are warm, and when they actually clash into each other, okay, they want to clash into each other. Let me say that what I'll do is I'll take up this and I'll put it in a horizontal way. Let us say I'll put it in this particular way. So this is the polar area, this is the equatorial area. I have heavier particles coming, I have lighter particles coming. Now what do you think is going to happen when they clash into each other? The lighter particles will rise up. Rise up in the sense they will be, say, mechanically pushed up. They will be mechanically pushed up basically because the colder particles are going to go down. Okay, they push themselves under this. And as they push themselves under this, the lighter particles are going to be tucked up or pushed up. They go up here, and of course they get colder. Okay, and you'll see that a sizable number of them starts moving towards the poles and back here, and these cold particles again come down here in the form of, okay, thus leaving us with 3 pressure belts as such. Okay, as I said, it has 3 convective cells, not pressure belts. Sorry, absolutely sorry about it. Now, where should I explain to you? Okay, as I said that this is a thermal pressure belt. This one is a thermal pressure belt. This is a mechanical one. Okay, because along these areas, or let us say along, yeah, any question? Somebody has unmuted himself or herself. Okay, I am referring to these boundaries in this diagram. Okay, so 2 thermally initiated cells and 1 mechanically initiated cells in each hemisphere. Lead to formation of pressure belts. I will try to put up the whole thing once again in a, okay, we'll see now what is going to happen here. I'll just try to draw those convective cells once again here. This is the low pressure area. Okay, particles going up from here. They move towards the respective poles. They're going to come down here, and then once they come down here, they move this way, they move this way, they move this way. Sorry. They'll move this way. Excuse me for that untidiness, and this way. So this is the Hadley cell of the northern hemisphere. This is the Hadley cell of the southern hemisphere. Complete. Okay. This is, both of them are thermal in each hemisphere. We're going to look into the next thermal now. I'll draw only one of them. Okay, you'll see that the heavy particles are going to come down here at the poles, and they start moving towards the lower latitudes. Now what happens here is that these warm particles and these cold particles, they meet each other along the subpolar low. This is going to push it up, and this is going to tuck itself down. When this goes up, this is going to move in this direction, and this is going to move in this direction, and coming down here, completing the respective cells. So this is going to be the ferrule cell, which is a mechanical cell. It's not a thermal cell. And of course, this is going to be the polar cell. Okay. Then I'll just also show you a few more things. Yeah. Okay. I'll do. Yeah. If anybody is posting any comments, please unmute yourself and let me know about that. Now there is one more interesting thing which we have not spoken about, and we should not have spoken about it to confuse ourselves, but I think we will have to. Okay, in 3 dimension, this is how it would look. And you'll see that wherever you have low pressures, low pressure belts, you would have those whitey, cottonish mm, uh, clouds as such. Okay, you'll see that you will have them in two places. You'll have them in the equatorial low pressure belt. You will have them in subpolar low pressure belt, but you will not have them in the subtropical high pressure. What are these clouds about? These clouds are related to rainfall. Rainfall is related to low pressure. Wherever you have low pressure, you will have rainfall. Okay. And how does this happen? Let me tell you that while the air particles are going up, if you remember the heat budget, and if you remember the convection and evaporation put together, okay, it's not only the air particles which are traveling up, it is also water evaporated into water vapor. Now, water vapors gets condensed into water faster than the air particles getting converted into cold air particles. And water vapor, obviously, condensed water vapor is going to be heavier as compared to air particles. So, water particles can make their way back, but air particles cannot make their way back. As a consequence, what happens is air particles are pushed to move towards the poles as we have seen and forming those convective cells. But the clouds that have formed here will deposit rain back here. The clouds that form here because of condensation will deposit rains here. So the air particles moving in this direction and this direction are dry. Because they are dry, now see what happens. They're already dry, and when they come down, as they come down, they are going to get warm. And because they get warm, they are going to absorb and soak in whatever moisture is there in this particular belt. And that is one of the reasons we can pull out any world map and check it. That is one of the reasons that high pressure belts are known to be areas which have no rainfall. Low pressure belts are known to be areas which have rainfall. And in fact, the largest of the deserts of the world are found along these mid-latitude high pressure belts. That's basically because of lack of water in this particular area. So I've given you a lot of logic in connection to each other. And believe me, you'll have to remember it in that particular way to get the best of understanding of these whole processes as such. Okay. You'll see that the atmosphere is very much dynamic. It's all full of air particles. I'll just give you a gist of all of these things. The atmosphere is dynamic. It's full of air particles. And you'll see that these air particles get warmed up. Let me bring you back to this diagram. They get warmed up. And then you're going to have these convective cells. And it is these convective cells, two of which are thermal and one of them is mechanical, lead to formation of alternating pressure belts. Alternating pressure belts. You're going to have 3 low pressure belts. You're going to have 4 high pressure belts. Okay, this is all about pressure. We are still not speaking about the air winds, the global wind patterns as such. Because once again, before we go into the details of understanding those, I will have to, I'll just check where did I keep that? Yeah. Just give me some time. I have pasted a few YouTube clips and links here. I'm not very sure which of them is needed to be taken into consideration before we go ahead. Okay, but let me tell you that, okay, we spoke about this happening here. Okay, at 0 degrees, it is rising and that is why you have low pressure, and that is why you have the clouds here, and then it's descending down here. So this is your Hadley cell of the northern hemisphere. This is your Hadley cell in the southern hemisphere. Now within the cell, you'll see that the particles are moving straight. The particles are moving straight into the cell towards the equator. However, outside, you'll see that this arrow of trade winds is going like this. This is going like this. Here you have the westerlies which are going like this and like this. Now actually it should come straight, right? You have a difference of relief, or you have difference of values. You have a high value point here and you have a low value point here. Okay, it should move from high value to low value straight. Why is it that it should move like this or it should move like this as such? But this will happen. This will happen only in case there is something happening to it. Okay, while I set up the YouTube clips here, I want you all to think about what actually should be happening as such. I will,
Sir, Coriolis force.
yes, that's excellent. Okay, the Coriolis, Coriolis force. Okay, and one of these clips is Coriolis force. Now, we will please uh, bear with me. I will just check and put up a few things for you again. Uh, mm, okay, I will copy this, and what I'll do is I will come here. I will start YouTube. Sorry, I will paste it here. Control B. And let me see if fortunately we directly go to. This is the circulation thing. Okay, are you able to? You will not be able to see that. I will stop presenting that, and I will present you with the tab of global circulation. Let me share that for you, and now I will play it for you.
You drag, you drop. In this animation, we're going to look at global wind patterns and talk about the reasons why the air circulates the way it does, and also patterns of rising and sinking air and how that relates to precipitation. The engine that drives it all, I guess you could say, is the intense heating by the sun that occurs in the equator areas where the sun is shining at a very high angle of incidence. And this hot air near the equator, being less dense, rises upward. It rises upward and it moves toward the poles, and then it gradually sinks at about 30 degrees north and south latitude. So we create these big spinning circles of air that we call the Hadley cells. Now, near the equator where the air is rising, it loses its ability to hold moisture, and you get a band of high rainfall and low pressure because there's air leaving the equator. Where the air sinks, in these belts at around 30 degrees north and south, you get high pressure sinking air, which creates areas of clear skies and desert climates. Now, as this air circulates and tries to flow back toward the equator along the surface of the Earth, or as some of it heads toward the North Pole or toward the South Pole, the Coriolis effect, the spin of the Earth, causes it to bend and turn, and it's going to create the two big wind belts that prevail on our Earth, two out of three, the trade winds, northeast trade winds and southeast trade winds, and then the prevailing westerlies. Now these winds curve, and the way they do because of the Coriolis effect. The winds curve to the right of their path, north of the equator. They curve to the left of their path, south of the equator, and they end up flowing from east to west or from west to east. Now the other big factor is what's happening at the poles. At the poles, the air is cold, and the cold air wants to sink. And as that cold polar air sinks, it heads toward the equator and it bumps into this air heading toward the pole here and toward the South Pole here. And it creates an area of rising air, and again, rising air produces high precipitation belts at about 60 degrees north and about 60 degrees south latitude. At the poles themselves, the precipitation is quite modest because the air is sinking, and that creates low precipitation.
Okay.
If
That's
you
done
can't
now.
find
So
a way to make money while you sleep, you will have.
why does this all happen? I have explained to you majority of it as such. And now let us look into what Coriolis force is all about. I will just share this once again. I'll present it. Tab. There are two clips. I think we will be going a bit ahead of time today, but then that is what it's all about. We need to understand it right away.
What's going on here? Every time I throw the ball straight, it seems to bend to the side. No matter what I throw, no matter how straight I throw it, the ball seems to be curving. Maybe it has something to do with this. That whole time I was spinning, which is why it looks like I'm about to puke. That curve is created by the Coriolis effect. You may have heard that it makes water in the bathtub spiral down the drain a certain way, or that it determines the way a toilet flushes. That's actually wrong. Those are not caused by the Coriolis effect. But the Coriolis effect is what makes hurricanes spin, and it's the reason why Jupiter's Great Red Spot is spinning the way that it is. So what is the Coriolis effect? Well, it's what happens when objects moving in a straight line appear to curve because you are rotating. And it affects all kinds of things. It bends the paths of missiles and sniper shots. But how does it work, and how does it create hurricanes? Right now, it seems like the ball's curving, but let's take a look at what's really happening. My friends and I put together this little experiment using a sort of spinning seesaw. Here, the camera's standing still. It's just hanging from the ceiling. And watch what happens. From the moment the ball leaves my hand, it's just going straight. Let's watch that again, frame by frame. Keep your eye on the ball. You can see it travels in a perfectly straight line. But what if you're spinning with the seesaw? Look at what happens when you rotate the footage so the seesaw stays sideways and everything moves around it. Now let's follow the path of the ball again, but from this new perspective. The trajectory looks completely different. Now let's watch this one frame by frame. From this rotating perspective, it totally looks like the ball is curving. That's crazy because you already saw that exact same throw. Watch it again on the left. The ball is going straight, but on the right, when you're rotating with the seesaw, the ball really looks like it's curving. You might be thinking, why should I care? I don't spend a lot of time on a spinning seesaw or on a merry-go-round. But you kind of are on a merry-go-round. The Earth is constantly spinning. Have you ever seen someone in a movie making fine adjustments on their gun? Well, one effect they're correcting for is the Coriolis effect. The longest sniper shot, which was over 3,000 yards, would have had to correct for a 1-foot deviation due to the Coriolis effect. So how does the Coriolis effect create hurricanes? Hurricanes form when air rushes from all directions into a low pressure region. So imagine there's a low pressure region between the two of us. Air is going to rush toward the center. Let's see what that looks like from space, from our camera that's not spinning, so the air or the balls are clearly going in a straight line. But if you're with the seesaw, you'll see the air bend to the right. In the northern hemisphere, this creates hurricanes with counterclockwise spirals. In the southern hemisphere, it does the opposite. It creates hurricanes with clockwise spirals. This storm on Jupiter, which is actually bigger than the Earth itself, has been spinning for at least 200 years, largely due to the Coriolis effect. So when you're in a rotating frame, the Coriolis effect seems to exert a very real force on objects. But there is no force. What you observe is just a result of your perspective. And you might be wondering, if this is simply a product of your frame of reference, then could other forces like gravity or electromagnetism also just be products of your frame of reference, of where we live in the universe or in the multiverse? For more on that, check out our video, Do We Live in the Multiverse? There are talking fish. And if you want to find out when...
So that was one explanation. We'll come up with another one.
But Grammarly can help. This sentence is grammatically correct.
With a simple game of catch, I think I've found a way to show an effect that will have you doubting your very own eyes. Now, they don't know it yet, but our budding ball players sitting on our specially rigged merry-go-round are about to demonstrate a rather astonishing optical illusion.
Right, here's the game, right? You're going to throw the ball straight to, what's your name, Victor, right? Yeah. But this time, I'm going to complicate things slightly. I'm going to rotate the merry-go-round counterclockwise. So you throw it whilst it's moving. What's going to happen?
I don't know why, but I feel like if we're going fast enough,
Yeah.
like I might actually be the one catching the ball.
Okay, so you're going to throw it and you're going to catch it. All right.
Yeah,
Right, what's going to happen, dude?
I was going to veer off to the left.
So the ball is going to swerve off to the left.
Yep.
And you might catch it.
Possibly.
Okay, good. Right, so what's going to happen?
I think it's just going to come straight to me, and I'm going to catch it like the champion that I am.
Show me the catch. Okay, great. Right, okay, is that everyone? No, hang on, one more.
He's
Spencer.
not arrogant.
Just quietly
He's
confident.
not catching it. He's
Really?
not catching it, no.
So what's going to happen to the ball?
I'm catching it. It's right here.
Great, so we've got one saying to go off to you, one saying to come to you, Spencer, and you think it goes straight ahead, but you think you'll be the one catching it.
Yeah.
Now remember, the ball will be thrown straight across the spinning merry-go-round, but where will it end up? Will it be caught by the thrower? Will it be caught by the person opposite? Will it be caught by the person to the thrower's left? Or by the person to the thrower's right?
Right, in your own time, throw the ball.
I got this. Oh!
So the answer was D. It was caught by the person on the thrower's right. Our camera angles seem to show the ball bend in the air. So is that a camera effect, or are we seeing what they saw?
Hang on, this couldn't get much more simple. The idea was just to throw the ball straight to Victor to show us his amazing catching skills.
That's right.
Yeah, it did. It just curved right over this way.
So let me get this straight. So you threw the ball, it left your hands, and then what?
And then it just got sucked over to him.
In the air.
Yeah, I threw a perfect throw.
What did you see?
Yeah, curved right in.
Right, so we're all agreeing here the ball curved in midair.
Yeah.
Yes.
And you didn't cheat this at all?
No, I didn't.
Okay. And do you know why it did that?
No.
Nope.
No idea.
It's called the Coriolis effect. And it's very simple. It's objects in motion appearing to be, it's an optical illusion, appearing to be deflected off their intended course. So what's actually happening here is you are throwing this ball. You can only throw a ball in a straight line. Can I clear that up straight away?
Yes.
Even though it appears in your eyes to be bending. So you throw the ball straight, it's still going straight, but the table is moving below you, and all of a sudden, look who's in front of that straight moving ball, and it looks like it's bent off to the right because you're still looking at the guy you were intending to throw it to, and that, ladies and gentlemen, is the Coriolis effect.
So these were the two things which relatively explain the Coriolis force. When we meet for an extra lecture tomorrow, you'll have to give me the time when we could meet. Not today, of course, tomorrow. We will go into the details of the Coriolis force and how it tends to generate all these global winds for us. That's all for today from me. If you have any questions for me of all that I had done. Yes, I see a question in the comment box, but it's too long to be understood at this scale by me too. I'll just go through it and I'll understand the context of the question and I'll come back to you when we meet tomorrow. Besides that, if you have any questions for me, you could just unmute yourself and ask your question. You can go ahead with your question, please. If you have no questions for me, that's all for the day then. We'll meet next time. That's tomorrow for an extra lecture. And once you have decided the time, I'll post the time on the group, probably in the evening, if there is no emergency on my side as such. So that's all for today. Thank you very much. You can leave the meeting.